This is where we are trying to get. We are trying to get to the quantum model of the atom. So how do we get from the Bohr model to what you see here? We have defined probability clouds, which are places where electrons could possibly be around the nucleus. The first thing I want to point out in this diagram is that each little red dot you see does not represent an electron. It represents a possible position for an electron to occupy. Now notice the density of where an electron might be, the darker color, is closer to the nucleus. This should make sense because electrons are negatively charged and the nucleus is positively charged. Opposites attract. So there should be more probable positions for electrons closer to the nucleus. All right, we are almost there. Here's another diagram of what the quantum model of an atom might look like. This is what we're trying to explain. How do we get there? Remember, Planck tells us that the electromagnetic radiation is quantized. Einstein explained that light acts as a particle. Then Bohr explained exactly where an electron can be around a nucleus. Then we have de Broglie asking us that question. If waves act as particles, can particles act like waves? We have to take all of these concepts and put them together to create the quantum model. It took many brilliant minds to develop the quantum model. That is why there is no one name associated with the modern model of the atom. Here are some more representations of what we're trying to get to. Okay, there are two more scientists that made contributions to the modern model of the atom. Erwin Schrodinger derived the wave function for an electron. He took de Broglie's ideas and developed a wave function for the electron particle. Here is that wave function. To me, this is gibberish. I have no idea what this means. All I know is that it describes the most probable positions for an electron to occupy in three-dimensional space around the nucleus. Long story short, Schrodinger did the math for the quantum model, thinking of the electron as a three-dimensional wave. The last piece of the quantum model puzzle was filled in by Werner Heisenberg. He developed a relationship between the particle nature of an electron and the wave nature of an electron. Here is his equation, the Heisenberg uncertainty principle. The equation basically says that you can try to determine the exact position of an electron, but as you do so, you become more and more uncertain of the electron's momentum, and vice versa. The position of an electron is a wave characteristic, and the momentum of an electron is a particle characteristic. Heisenberg provided a relationship between the particle and wave nature of an electron. Putting all of these ideas together is what led to the quantum model. Once again, here's a diagram of a quantum model. So what does this mean? Look at this diagram as a cross-section of an atom. Somewhere in the center you will find the nucleus. Each spherical region represents a possible position where an electron could be. You will notice that these spheres are a certain distance away from the nucleus, just like Bohr's energy levels. Remember that each individual dot represents a probable position for an electron, not an electron itself. These positions are based on Schrodinger's wave equation. When you put electrons in these orbits, their wave-like properties start to interfere with one another. Constructive interference creates the areas of probability, the blue dots. Destructive interference creates the nodes, or white areas, in between the blue dots. What we see here is constructive interference for a three-dimensional wave, which would create a sphere. You may remember it as an s orbital. There are also p, d, and f orbitals, which are created by electrons with higher energies. The probability cloud you see here would contain the electrons with the lowest energy. They are closer to the nucleus, so they have the lowest energy. If an electron were to gain a quanta of energy, it could move to one of the probability regions further away from the nucleus. This is where Planck comes into play. Now, how do you visualize the quantum model of the atom? I think the best way to think about the quantum model is my last example here, like a spinning coin. When you spin a coin, you know the coin is there, and it really only exists in two spots. But it looks like it occupies a three-dimensional region. Two-dimensionally, spinning fan blades work well. If you focus on one blade, you can follow it and tell where it is, but you don't fully understand how fast the fan blades are moving. If you focus on how fast it is moving, you can't pick out the individual fan blades.